Have you ever really stopped to think about how your thermostat keeps the temperature just right? I mean, perfectly steady. Or how your car's cruise control can hold its speed no matter if you're going up a steep hill or down one? Well, behind all of that, there's a tiny, invisible brain running the whole show. It's an automatic controller, making countless little decisions every single second. And today, we're going to pop the hood and see exactly how it works. All right, so here's our game plan. First, we'll see just how unbelievably common these controllers are. Then, we're going to break down the secret 3-part recipe that makes them tick. After that, we'll get into the real art and science of tuning them perfectly. We'll even see what happens when a system has to juggle conflicting goals. And finally, we'll look at how this smarter control is actually building a smarter world. So let's kick things off with the most basic problem that control systems have to solve. How do you make something, literally anything, automatically stay at a target value without a person having to stand there and fiddle with the dials all day?
I mean, think about it. These things seem worlds apart, right? You've got a massive industrial factory, your car on the highway, and that little white box on your living room wall. But secretly, they are all wrestling with the exact same fundamental challenge. So what is the common thread here?
The answer is something called a PID controller. And get this, as you can see here, more than half of all industrial controllers in the world are based on this one single idea. In an age of mind-bendingly complex AI and machine learning, you might wonder why this simple concept is still king. Well, it's because it's just so incredibly robust. It's the elegant, unsung hero that's quietly running our entire modern world. So what in the world is a PID controller? Honestly, the best way to think about it is like a simple 3-part recipe. It's a recipe for achieving perfect balance and perfect control. So let's break down those ingredients. The absolute brilliance of this recipe is how it thinks about time. The P stands for proportional, and it's all about the present. It's constantly asking, how far off are we right now? If the error is big, it gives a big push. Then you have I for integral. This part looks at the past. It's like the system's memory, adding up all the tiny little errors over time to make sure there's no slow drift. And finally, D for derivative. This is the crystal ball. It predicts the future. It looks at how fast we're closing in on the target and taps the brakes just in time to stop us from flying right past it. Present, past, and future, all working in perfect harmony. But here's the catch, and it's a big one. Just having the P, the I, and the P isn't enough. They have to be perfectly balanced or tuned. If you get it right, your system is beautiful. It's stable, fast, and snaps back from disturbances. But if you get it wrong, oh boy, it can be a total mess, oscillating like crazy, responding at a snail's pace, or just completely overshooting the target. This tuning process, that's the real challenge. So that begs the question, right? How do engineers actually find that perfect balance? Well, this brings us to the fascinating art and science of tuning, and it all starts with a classic, really clever method that's been around for decades. So one of the go-to solutions is a technique called the Ziegler-Nichols method. Imagine you have a black box, a system where you don't really know the internal math. This method gives you a set of rules, a way to sort of poke and prod at that system to get a really, really solid educated guess for where to start with your P, I, and D values. And here are those rules. Now, don't worry, you don't need to memorize this table or anything, just appreciate the idea behind it. What engineers do is they carefully push the system, turning up a gain knob until it hits the exact point where it becomes unstable and starts to wobble. That wobble gives them a couple of magic numbers. Then they just plug those numbers into these formulas and poof, they've got their starting P, I, and D settings. It's a really clever, hands-on way to get in the ballpark. But remember I said in the ballpark? Well, here's why. In one of the examples from our source material, just using the Ziegler-Nichols rules straight out of the box caused the system to overshoot its target by a whopping 62%. For most things, that's not just bad, it's totally unacceptable. And this is where modern engineering really shines. After you get that initial guess from a method like Ziegler-Nichols, you then turn to computational tools to really fine-tune the parameters. In that very same example, engineers were able to take that huge 62% overshoot and, by tweaking the numbers on a computer, dial it all the way down to a much more manageable 18%. Okay, so we've pretty much figured out how to hit a single, stable target. But The real world is messy. It's complex. What happens when a controller has to juggle multiple and sometimes conflicting goals all at the same time? Exactly. Let's go back to your car's cruise control. You want it to be tough enough to quickly reject a disturbance, like when you hit a pothole, so you don't feel a sudden lurch. But you also want it to be smooth and gentle when you set a new speed. The problem is, a single set of tuning parameters that's great at one of those jobs is probably going to be pretty bad at the other. So what's the solution? It's a much more advanced approach called a 2 degrees of freedom controller. Now, forget the fancy name. Just think of it like giving the controller 2 separate mini-brains. One brain is a specialist at ignoring the bumps in the road. The other brain is a specialist at smoothly getting you to your new target speed. By separating the jobs, you can optimize for both without having to make a compromise. It's pretty slick. And this really brings us full circle. We've seen this incredible journey, right? We've gone from these clever experimental rules of thumb all the way to these advanced, computationally optimized designs that can handle a really complex and demanding world. So let's just do a quick recap of the big takeaways. First, PID controllers are those invisible brains, the workhorses in so many systems around us. Their real magic is that balancing act between the present, the past, and the future. Remember that tuning is the most critical part. It's everything. And while those classic rules give us a fantastic starting point, it's modern computers that really dial in the perfect solution. And finally, when the job gets tough, advanced 2DOS systems let us handle complex and conflicting goals. Which leaves us with this one last, really fascinating question to think about. For the better part of a century, we've used these amazing controllers to create stability in our world. But as automation keeps accelerating, weaving into every part of our lives, from self-driving cars to robotic surgery, what entirely new, unforeseen problems of balance, prediction, and control will we ask these invisible brains to solve next?